The Sylver coinage game is a two-player game where we're calling the first player Alice and the second player Bob. Each turn, Alice and Bob must name a number from 1 to infinity, but they can only name a number if it isn't the sum of previous numbers, and the first person to select 1 loses the game. For example, if Alex picks 7, then Bob can't name 7, 14, 21, and so on, because they can all be made by adding 7 multiple times. If Bob picks 5, then Alice won't be able to pick 12 because it can be made by adding 5 and 7. Similarly, she can't pick 41 either because it can be made by adding 5 4 times and 7 3 times. Lastly, if Alice picks 9, the number 23 can't be made because it's the sum of 5, 7, and 9. Now that both Alice and Bob know the rules of the game, Alice decides to start for real. So she picks 10 to the 10 to the 10. And then Bob picks 100 to the 100 to the 100 to the 100 plus 1. At this point, Bob and Alice realize that this game will take a while, and so they decide to start all over again, but with a new goal. This time they want to see which numbers are winning numbers, starting from small numbers and working their way up. So Alice starts with the number 2. When Alice picks 2, the numbers 2, 4, 6, 8, and so on can't be selected anymore because they're multiples of 2. Bob responds by selecting 3, which removes 6 and 9, but it also removes 5 and 7 because they can be created by adding 2 to 3 and then adding 2 to 5. And after that, there are no other numbers remaining except for 1. And once Alice picks 1, she'll lose the game. So therefore, the optimal response to 2 is 3 and Bob will win. So what we see so far is that if Alice picks 2 and Bob responds with 3, Bob will win. But what if Alice plays 3 first? What will Bob play, and who will win? Does the order matter? No, it doesn't actually, because if Alice plays 3, Bob will respond with 2, and the number of coins remaining will only be 1, and once Alice selects it, she'll lose the game. Another important thing to notice about the numbers 2 and 3 is that regardless of the sequence of moves played up to that point, whoever plays 3 or 2 first will lose the game. This is because at this point, there will be no other numbers remaining except the number 1. So far we see that Alice will lose if she picks the numbers 1, 2, or 3, and Bob wins by using the pairing strategy for 2 and 3. So the next number to check is the number 4. If Alice picks 4, then the optimal move for Bob is to play 6. This forms 2 columns. Now, Bob can use a pairing strategy to win this game. For example, if Alice picks 13, then Bob will pick 15. If Alice then follows by picking 7, Bob will pick 5. And at this point, Alice will have to pick 2 or 3, and then Bob will pick the other number, and then Alice will be forced to pick 1 and lose the game. So far, all the numbers checked so far are wins for Bob. This is by using a pairing strategy. There are also pairing strategies for higher numbers, such as 8 and 12. If Alice picks the number 8, then the optimal move for Bob is to pick the number 12. And then there's a pairing strategy that Bob can utilize. If Alice picks a number in the orange columns, then Bob should pick a number in the other corresponding orange column. Similarly for the purple and the blue columns. Unlike the simple 4-6 example, there are 3 different colored columns. So you might be worried that picking a number, say, in the purple column, might eliminate a number in the orange and blue column and break the pairing strategy. For example, if Alice picks 17, this removes the number 34, because it's equal to 17 plus 17. So, unless the number 38 is removed, the pairing strategy will be broken. Fortunately, the pair for 17 is 19, and it does actually remove the number 38. To understand why this pairing strategy works, first recognize that all numbers can be written as 8 times r plus c, where r is the row and c is the column. For example, the number 14 is on the first row and is in the 6th column. The number 3 is in the 0th row and in the 3rd column. And the number 8 is in the first row and the 0th column. All the numbers in the purple column can be written as 8r plus 1, where 1 represents the first column. The effect of adding 8 to this column just increases the row count by 1. Similarly, adding 8 to the crosshatched purple column will also increase the row count by 1. Therefore, pairing in the purple columns will also eliminate pairs in the next row down. Similarly, if we add 12 to a number in the solid purple column, we notice that the row count increases by 1, and we affect the fifth blue column. Adding 12 to the purple crossed hatch column, we notice that we eliminate a number in the seventh column, and therefore pairing the purple columns removes a pair in the blue columns. Lastly, adding a number in the purple column twice will give a number in the orange column, and the same pattern appears in the crossed hatch counterpart. This analysis shows that removing numbers in the purple columns will also remove numbers in the other columns as well in pairs. The same method can be applied to the orange and blue columns, and you'll see that this pairing strategy does indeed work. For the numbers less than 8, there's also a pairing strategy. Pairing together the numbers 2 and 3, 4 and 6, and 5 and 7, along with the column pairing, is enough to ensure that Bob will win. There is also a more complicated pairing strategy for the pairs 9 and 6. If Alice plays 6 and Bob plays 9, then Bob needs to pair numbers on the purple columns and the orange columns to win this game. Additionally, there's a pairing strategy for the lower numbers that changes depending on which pair is played first. If the pair 4-11 is played first, then Bob should pair 5 and 7 after. Likewise, if the pair 5-8 is played first, Bob should pair 4 and 7. And if the pair 7-10 is played first, then Bob should try to pair 4 and 5 and 8 and 11. So far, all the numbers inspected so far are winning moves for Bob, but 5 is actually the first winning move for Alice. To see why 5 is so special, we should see some responses from Bob and see what patterns emerge. In this example, Bob plays 9, and the purple boxes are just all the numbers that are multiples of 9. The first thing you might notice is that there are no columns like the previous examples, where Bob could use a pairing strategy to win the game. If we look at other possible moves for Bob, we see that this pattern continues, regardless of what Bob decides to play. Another pattern you might have noticed is how long does it take before a multiple of 6 appears in the same column again. For example, the number 0, you need to add 6 5 times before you reappear in the 0th column again, at number 30. At the number 6, you need to add 6 5 times to return to column 1 at 36. And this pattern continues for all columns. Also notice that every time you move down a row, you're adding 5 to that number. So at 12, you add 5, you go down to 17, which is the number right below it. If we repeatedly add 5, we'll eventually hit 42. But also adding 6 multiple times from 12 also leads to 42. Therefore, adding 6 multiple times eventually becomes a multiple of 5. In this example, it's obvious that adding 6 5 times is a multiple of 5. Understanding how many times we have to add a number before it becomes a multiple of another number will explain why we see this pattern. As a simple example, let's assume that Alice picks 6 and Bob picks 10. Notice that the greatest common factor between these two numbers is 2. In this case, adding 10 3 times is enough to be a multiple of 6. Generally, let's assume that Alice picks capital A and Bob picks capital B, and they share common factor C. In this case, adding capital B small a times will be a multiple of capital A. Notice that small a times big B can be rewritten as small a times CB, and the factor C, along with small a, is being used to construct large A. Notice as a special case that if C is equal to 1, then we have to add B a times so it becomes a multiple of A. Prime numbers are numbers that can only be written as the product of 1 and itself. Therefore, if Alice picks a prime number and then Bob picks B, the greatest common factor will be 1, because if it wasn't, that means that B is already a multiple of P, which is an illegal move. For example, if Alice picks 5 and Bob picks 15, 15 can be constructed by adding 5 3 times, and therefore would be a legal move. And therefore, we need to add B P times, so it's a multiple of P. In this example, where Alice picks 5 and Bob picks 6, we know that we need to add 6 5 times to become a multiple of 5. The orange number at the top counts how many times 6 has to be added before it reappears in this column, since moving down a column is the same as adding 5 multiple times, i.e. a multiple of 5. Notice that before revisiting a column, all their columns need to be visited once. Another pattern that you might have noticed is that after A and B has been selected, there are only finitely many options left when A is a prime number. The question you might be asking is, what is the largest number remaining? In this example, we know that we appear in the 0th column the first time by adding 6 5 times, and we land on the number 30. By subtracting 6, we return to the previous purple box, which contains the number 24, and by moving up a row, by subtracting 5, we get the largest remaining number. In this example, Alice picks 5 and Bob picks 6, so the largest remaining number is 19. Generally, if the largest common factor of A and B is 1, then the largest remaining number is A minus 1 times B minus A. This result was first proven by James Joseph Sylvester, and is actually the reason why this game is called the Sylver coinage game. What we have shown so far is that if Alice picks a prime, such as 5, then, after Bob picks B, there will only be finally many moves remaining. And we've determined the equation for determining the largest remaining number. Using the largest remaining number, it will show that Alice does have a strategy to win this game. If Alice picks a prime A, and Bob picks a number B, then the largest remaining number L is either a winning move for Alice or a losing move for Alice. If L is a winning move, then obviously Alice will play L and will win the game. But if L isn't a winning move and is actually a losing move, then Bob will win the game by playing some response R. But in this case, Alice could have won if instead of playing L, she played R before Bob did. Therefore, Alice wins by either playing L or by stealing R before Bob can play it. To understand why L is so special, let's see which numbers eliminate L when selected. If we select any number in the fourth column, by repeatedly adding 5, we'll eventually eliminate L. If we pick a number in the third column and add 6, we'll be in the fourth column, and then by repeatedly adding 5, we'll eventually eliminate L. This pattern also holds for column 1 and 2, by repeatedly adding 6 until you get to the fourth column, and then adding 5 until you eliminate L. In this example, where Alice plays 5 and Bob plays 6, it just so happens that L is the winning move for Alice. In this game, if the first two moves are 5 and 7, and Alice plays 23, then Bob will win by playing 8. He'll win by using a pairing strategy for the remaining numbers. Now, notice what happens if Alice plays 8 before Bob, instead of playing 23. The position looks exactly the same as before, except now it's Bob's turn to move instead of Alice's. Now Alice can use the pairing strategy to win this game instead of Bob. What we've shown is that Alice is winning if she picks a prime greater than 5 for her first move. Indirectly, we have also shown that if Alice plays 10, then Bob wins by playing 5. This is because there is the same coins available as if Bob played first the number 5, and we know that 5 is a winning move. Using the same reasoning, we also know that if Alice plays 14, Bob wins by playing 7, and if Alice plays 15, Bob wins by playing 5. Generally, this means that all composite numbers with a prime factor greater than 5 is a win for Bob. The next smallest number that we haven't determined who wins is the number 16. As an exercise, spend some time to think about who wins if Alice plays 16 on her first move. Notice that 16 is not a prime number, and it doesn't contain any prime factors greater than 5. The inventor of the game, John Conway, is actually offering $1,000 for anyone who determines who wins after Alice plays 16. But for now, the problem remains unsolved.